Very pleased to now introduce Dr. John Tracy, who served as task force. For a lot of you who have worked with Dr. Tracy, I won't bore you with all his details. You know him a lot better than I do, so you could probably introduce him. But just to hit highlights, he is director of the Texas Water Resource Institute, a member of the Texas A&M Civil Engineering faculty, has worked previously in Idaho and other places, is well known for his work in this area, and I want to recognize a couple people. Dr. David Baltensperger is a member of the CAS board at Texas A&M, and I have to give David credit because he was the one that helped me recruit John to do this project. So I want to thank him. He served as the liaison to this effort. But we appreciate Dr. Tracy and the work of, and he will introduce some of the other folks who contributed to this effort and talk about kind of the key findings and the highlights of the paper. We're going to follow that by a number of you who have agreed to serve on kind of a brief panel to look at this and kind of share some of what's happening relative to these aquifer depletion issues in your particular states, and then we'll open it up for some question and answer. So, John, I'll turn it over to you.
Thanks, Ken. So this one for the...
It's on, yeah.
Yeah, okay. Yeah, there we go. So I was the task force chair. I guess makes me the lead author, although I don't know how much I actually wrote. I mostly edited things. The writing panel, the task force, was made up of a variety of people from federal government reclamation. Lenny Conoco, who's in the room with the USGS. I think he's the only other person on the writing team who's actually in DC for this rollout, so he can answer quite a few questions on this. And then several faculty from A&M and also from University of Nebraska. And hence there's probably a heavy emphasis on issues in the Ogallala region, which is one of the aquifers experiencing the greatest depletion. I also want to thank the reviewers. Their comments were really helpful and really aided in getting the paper together. That was Mike Campana, a lot of you know him, Jay Lund, a lot of you know him, and then CJ Olson with USGS. I don't know if many of you know her, but she was very useful in the review also. And then David for his liaison role with the CAS. So, this is where I was starting it out for the house, and so I can kind of blow through the first couple slides because I thought it was a good idea to define what groundwater is and not go back to the old days of Mr. Science and say water is groundwater, you know, sort of through a grinding machine. No. But groundwater is, practically speaking, water that exists in pore spaces at pressures greater than atmospheric. And the way I always taught at Colorado State when Dan Sonata taught us was, if you dig a hole and water starts coming in, you found groundwater. So that's kind of like the practical definition of groundwater. But he also told us just because you found groundwater doesn't mean you have an aquifer. That is, an aquifer, it is a series of formations that can actually hold enough water and bear enough water for it to be useful. So it's a somewhat relative definition because I own a home in Idaho. We have a homeowner's well, and we pull water from an aquifer, and that aquifer is plenty big and sustainable for us. But if you put a well in there to irrigate 640 acres, probably not. And so, you know, this definition of an aquifer, of having sufficient quantity of water and able to sort of transmit that water, it's what's an aquifer for a home may not be an aquifer for a big agricultural production region. So we need to understand that. And then there's all kinds of types of aquifers, and we get into the two major types. Unconfined, which means you sort of have a free surface, and if water is coming down into the aquifer, the surface rises up, and if you pump it and the surface goes down, the surface is free to move. And a confined aquifer, which exists between impermeable materials, and so the groundwater in confined aquifers tends to be under higher pressure. And then you can kind of get into all sorts of sub-definitions where you talk about alluvial aquifers or artesian aquifers or all sorts of other types. But those are the two major types. One thing that I thought was important was actually discussing where groundwater sits in the hydrologic cycle. And this is sort of comes in because of many conversations I've had in the states I've worked in, from everywhere from California to Nevada to Kansas to Idaho to Texas and on and on. And the reason is that a lot of discussions, we seem to understand groundwater through visualizing surface water, and this creates a problem. And so from the USGS, they have this wonderful diagram and also this very good information talking about all the water that exists on Earth and what forms it exists in. And the thing that to remember here is that at any one time, this is where the water is, but water's constantly moving through the cycle. So about 97.5% is saline water, most of it in the oceans, but some brackish groundwater, saline groundwater. So if we go to freshwater, we say it's 2.5%. But remember, that's just at any one time. The water in the ocean is constantly evaporating, it's constantly going in the atmosphere and flowing down, so it's not like ocean water is unusable. We use it, it's just at any one time, this is where the water is. So if we think about freshwater and 2.5%, where is all of this? If you look at the streams, very, 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 very small fraction. However, water doesn't sit in streams too long. The residence time in streams is hours to weeks. That is, once it gets in a stream and starts moving downstream, it pretty much keeps moving until it runs into an ocean or runs into a lake or drains to groundwater or wherever. So then we look at lakes and say, well, that's a higher percentage, but 0.3% of the available freshwater supply is not all that much, considering that a large amount of that sits in Lake Baikal in the middle of Siberia. And realizing that when you say, how long does water sit in lakes? Months to years. Now, Lake Baikal can actually go into decades, and there's certain lakes like that. But overall, we're talking about relatively quick periods of time, and especially when you think about it in terms of how long we've had monitoring networks out there. That is, USGS has had stream monitoring networks, lake monitoring networks, groundwater monitoring networks, and they've been in place for over a century. And so when you start looking at these residence times, you realize we've had enough information to understand the behavior of these systems, and not just where the water is, but sort of these cycles of when they have water and when there's high water and low water. And then we move into groundwater. And that's about a third, not quite a third, but it's about 30% of the available freshwater supplies across the world. Well, the problem is that the residence time of groundwater can be short, can be years, like the Edwards Aquifer is fairly responsive, but it also can be millennia, that there's certain aquifers and groundwater's dated to thousands and thousands of years old. So if you think about that in terms of what we know about groundwater, putting in monitoring networks tells us where it is, but have the networks been in there long enough to actually go through the cycle of the residence time through groundwater? That sort of creates this interesting issue in terms of what we know about groundwater in terms of its temporal variability and what we know about surface water in terms of its temporal variability. We have records long enough to understand the temporal variability of surface water. We really don't have records long enough to tell us the temporal variability of groundwater. Now, there's some really unique tools that have been out there for age dating that tell us a lot more, but in terms of actually having the records of what's been going on in all the aquifers all the time, some of these aquifers, we have very short monitoring records relative to how long the water's been in the aquifer. Then we talk about the other sources of fresh water, and over 2/3 of fresh water is locked up in ice caps and glaciers. And the reason I put that separate is that while there have been some unique technologies that have tried to tap into this as a water supply, they're not widely used, and especially in agriculture. And then in the atmosphere, there's more water in the atmosphere than there is in streams at any given time. And again, there's some really unique technology that's being used to tap directly from atmospheric water and turn it into fresh water, but it's not something that's particularly used in a wide variety of applications, nor is it used for agriculture. So when we really think about where's water being used to support irrigated agriculture, it comes from stream, lakes, and groundwater. When we look at it, the vast majority of that water is in groundwater. But when we start looking at residence times and understanding what we have in the streams is sort of very short residence times, lakes a bit longer, but groundwater can extend from much, much longer than we've actually been using irrigated agriculture in many of these systems. So in terms of groundwater use, this is USGS water use papers, which are incredibly useful. And it would be nice to get even more data in these, but this is surveys that the USGS does with all the states across the nation, and they've been doing these since 1950. And the data that's been collected has been going on for, what does that make it now, 65 years. And when we are able to look at it, these water use surveys, they survey use of how much groundwater is being used and what's it being used for, agricultural, municipal, industrial type thing. So if you look at it, there's been this really big increase in groundwater use from about 1950 to about the 1980s. And the use has increased threefold. And in particular, the use in agriculture has increased a little over threefold. And sort of what drove that? Well, quite simply, there were two things that drove it. The invention of the centrifugal pump that allowed for larger quantities of groundwater to be pumped from deeper depths in a power-efficient manner. And then rural electrification, that is the reaching out across all parts of America for everybody to have access to reliable, relatively cheap forms of electricity. You put those two things together, and all of a sudden it was cost-effective to extract groundwater from much deeper depths, and not just from those locations where groundwater was relatively close to the surface or you had an artesian aquifer. So that's what drove this development. Now, what I also like to point out is that this really went up until about 1985, and then since then, it's remained relatively flat. That is, there's this perception that since groundwater declines have happened in places like the Ogallala and continue to happen in Central Valley of California and the Mississippi Embayment, oh, we must be pumping more groundwater. No, we're pumping about the same as we did 30 years ago. The difference is, and this kind of again comes into sort of this response time of groundwater, is that the declines have been happening and they kept happening, and groundwater is so consistent in terms of how long it takes for things to respond relative to how we think about surface water management, that it's finally hit the point of, oh, we got a problem here, we got to do something about it. And it really isn't surprising. People were aware of this back in the 80s. It wasn't like people were blind to it. However, I think the awareness was more in the scientific community rather than the policy community and just sort of general society. And so this is where people are starting to really say, okay, we've got to think about this and decide what to do about it. Where is this occurring? The interesting thing is, and again, this is actually right out of one of Lenny Conoco's studies, and I cannot tell you how many times I've used this figure in presentations. Thank you for putting this together. And it looks at the aquifer depletion at various major aquifers across the country. And it sort of does this in terms of the total volume of water depleted in a term of cubic kilometers, which is, a cubic kilometer is a lot of water. And if you look at the two areas with the highest amount, highest volume of depletion, it's the Ogallala and the Mississippi Embayment. The Central Valley of California and the Arizona alluvial aquifers, they've had a significant amount of depletion. And as Lenny states in the paper, the highest depletion is the Ogallala and Mississippi Embayments, but the highest intensity of depletion, which is sort of relative to how quickly it's being depleted, is in the Central Valley of California. It's really, causing problems. If you notice up in the Pacific Northwest, that's actually negative depletion, or what we call accretion, rise in water levels. This is relative to 1900. And those aquifers are interesting because if you looked at this, there was a huge increase in groundwater storage in the Columbia Plateau and the Snake River Plain from about 1900 to the 1950s. But with the advent of the pumpage, things started changing, and if you actually looked at depletion since about 1960, 1970, even those areas have had issues with groundwater depletion they're having to deal with. And so groundwater depletion is something that is occurring everywhere across the United States and everywhere across the world. And we're now at the point where we not only recognize this, it's become something that policymakers realize they have to do something about, and water users are going to have to address what the consequences of this depletion are as we move forward. So what drives the depletion of groundwater? So when I think about this, a lot of times when we say, well, what's causing this, we talk about how it's happening. And that's not necessarily what's causing it. And so I like to think about this in terms of the physical drivers of depletion and how governance of groundwater and financial issues associated with extraction and use of groundwater all end up driving the situation of depletion. So if we go through a real simple diagram, we start looking at the simplest case of groundwater system with no pumpage, you may have a groundwater formation connected to something upstream, could be another aquifer, could be a stream, could be a lake, and the aquifer may be getting some recharge. And then at the downstream end, maybe it's discharging to a stream, and then you're getting some recharge from seepage from rainfall events or just water being able to seep down to the aquifer. And so you may have this slope of the water table, so the water's moving from left to right through the aquifer across the diagram. Well, then you put in a well and start pumping and you get drawdown. And so this changes everything. Now, the natural recharge from over the aquifer and an unconfined aquifer, that may stay the same. But by declining the water table, you're doing two things. One is you may be increasing the amount of recharge occurring from upstream, and you may be decreasing the amount of discharge to a water body downstream. And when we start looking at this volume of pumpage, and you say, well, I pumped water and I used it on my crops, where did that water come from? It's actually a mixture of this increase in recharge and decrease in discharge, and also the volume of water you're actually depleting in the aquifer. And so we can actually look at these two elements and say, well, the amount you're pumpage is a mixture of depletion, actually what you're taking out of the aquifer, and also capture, which is what you're taking away from other water bodies. And the lesson here is there's no free water. It's all out there. It's all water. And so when you're pulling water, you're taking it from someplace, and you just have to recognize this. Now, when you initially start pumpage, almost all of your water coming out of the well is from depletion. It takes a while for everything to react and change recharge and change discharge. And so early on, almost all of the water you're pumping is depletion. Later on, you see it more transitioning, and especially if it moves to a new stable condition, most of it's going to be coming from capture. But that provides another important lesson, is that when we start talking about groundwater depletion, there's this tendency to say, oh, that's bad, that's really bad. Well, you can't use any groundwater unless you deplete it first. That's the reality of using groundwater. So you just have to understand there's going to be some depletion, but what is an acceptable level and what is a sustainable level of depletion in the aquifer? And so you can't start putting value judgments on a term like depletion. You just have to understand and put it in context of what it means for sustainable water use as you're looking at groundwater use across these systems. So, governance and financial drivers. Well, there's some interesting drivers here, and in terms of the governance drivers, when we start looking across the western United States, all the surface waters are dominated by what is considered prior appropriations doctrine. And understanding that the states own all the water in the state, and the states get to decide what the rules are for people being able to use the water. And so a lot of the western states developed something referred to as prior appropriations, where the basic rules, and this is an oversimplification, but it's first in time, first in right, as long as you beneficially use the water. And what that means is that if you were out there and you go to a river and you say, hey, I'm gonna grow some crops and no one else is using the river, and you do conversion and prove that you're growing crops and making money and life is good, well, you're the first one in time. If somebody else even goes upstream and takes the water and starts harming you, you get to go and say, hey, you harmed me, we gotta fix this problem. And so many of these states brought groundwater under prior appropriations. Not all, but many of the states did. And the problem with that, with groundwater, is that with surface water, when you're out there in a year and you have water flowing, it's very easy to say, well, we diverted this much water, we have less water, we diverted, and you know when you run out of water. But when you drill a well, what does it mean to run out of water? Because you may be, let's say you're 40 foot down and pumping a well. Well, the next year you're 40.5 feet down, and the next year you're 41 feet down. So are you harming any other groundwater users? And by the time you get into the capture situation, you may be many years down the road when you finally realize, oh, our groundwater use is harming our surface water uses, and then you've got to put all that together to understand how to implement prior appropriations. The more difficult part of that is that if you're in a situation where you are using groundwater as a supplemental form of irrigation, that is, you try to do dryland farming, but you have some bad years where you're going to need groundwater to get your crops harvested. You get into a situation where what happens if you have 5 or 6 good years of rain in a row and you don't need groundwater? Well, the state engineer can come back and other water users can come back and say, well, you don't need groundwater, you're not using it for anything. You can actually lose your water right. A lot of states put a 5-year limit on prior appropriations. And that means if you didn't use it for 5 years, well, you don't need it, so we're gonna put somebody else in line. So you actually create an incentive for people to use groundwater, even if they don't need it, just to maintain their water right. Now, do groundwater users do this? Oh yeah. I mean, I've known groundwater users to say, we gotta pump some groundwater to prove that we're using this beneficially. That can create an incentive to use groundwater inefficiently and actually lead to depletion. The other situation in states like California, Texas, Nebraska, is you have something where groundwater is more considered, not necessarily, in Texas it is considered right of the landowner, but it's something which is not governed by prior appropriations. And so there you have groundwater seen as this common pool resource. And in many of these situations, it's called the law of the deepest well. That is, you go in and you pump, and it's not a prior appropriations. That is, if you can get it, you can use it. Sort of the right of capture of groundwater for use. Well, this can create a problem and create a prisoner's dilemma in the sense that if you're out there pumping and you don't know what your neighbor's pumping, you know he's pumping, but you don't know what he's pumping, and you see his crop is greener than yours, you're thinking, well, maybe he's pumping more water than me. Maybe I should pump that water, because if I don't pump that water, he'll get that water next year. And then you can get into a situation where everybody doesn't trust everybody else. In essence, they start overusing the resource because the logic is, well, if I'm good and I try to conserve, all that's going to do is benefit my neighbors, so why should I do that? So that's the problem that can come in when you're using something that's more associated with what we call correlative rights, or the right of capture, and you run into the common pool problem. So these are governance drivers that can actually create governance incentives to overuse groundwater and deplete aquifers. Then there's the financial drivers, and the problem that can occur in financial drivers is that when we're looking at groundwater use, and let's say you're actually set everything up and you're trying to be as efficient as possible, and you think, well, what are the consequences if I overwater by 10% versus underwater by 10%? What if I miss on the underside by 10% versus over? over 10%. You probably had to buy a little more fertilizer because you're leaching some out of the root zone. You're using a little more energy to provide that water, and so there are some added costs. But if you miss by the under 10%, you just lost your crop. So it's an asymmetric economic response, as they would call it. That is, the consequences of going under are so much severe than going over, you're going to tend to go over. And that's what can happen on the financial drivers. And in addition to that, which makes it very difficult, is you can buy crop insurance, even for irrigated land. But the problem with that is that for payouts to occur, you have to be using best accepted irrigated practices. And the best practices may lead to a situation where it's like, well, no, the best practices are making sure that you use a little more water, and so even if you tried to be as good as water as possible, you always run the risk of having crop failure and then the insurance not pay out. And so this creates some financial incentives to overwater, because again, you're paying a little more for it and you'd like not to, but the consequences of missing are too severe to really run the risk there. So, what are the consequences? And I should have never put this slide in. I'm just going to go to consequences. So when I went back and looked at my groundwater notes, I noticed that every single idealization of an aquifer, we had this nice horizontal flat bottom in the aquifer, and maybe we had a slope of the aquifer table. And it finally occurred to me, this isn't the reality of aquifers. The bottom of the aquifer, in essence, the impermeable lower level tends not to be nice and horizontal. It tends to have some slope to it. And when you look at the Central Valley of California, when you look at the Ogallala, that's the reality. So if we go into a situation where we say, okay, 3 pumpers come in, nobody's developed any groundwater yet, and they're all going to say, hey, we've got an aquifer here, let's start pumping and irrigating some crops. You got A, B, and C. Now the thing is when they go in, maybe they didn't have perfect information, so everybody just drilled a well and said, oh, hit water, life is good. The costs associated for using groundwater for A, B, and C in year 1 are almost the same. B may have incurred a little higher cost because they have a deeper well, but basically there's not a whole lot of economic difference or consequences for pumping water here. It's pretty equal. But then you go on decades later, and you realize that just by the nature of where A, B, and C located their wells, the costs of pumping increase for B. That is, they have to lift water a higher level. So they're definitely paying more for the water, but it's marginally more. They still have access, they don't have to do anything with the well, they just have to use more energy to get the water they want. C, on the other hand, didn't drill the well deep enough, bad on them, but they realized, well, they can drill the well deeper. Now it can be a very expensive proposition, and so the costs associated with groundwater depletion for C are much higher than B. And then you got poor A, where you're out of luck. That is, there's nothing you're going to do there other than maybe horizontal drill into somebody else's on property, which can lead to all sorts of other nastiness and problems. And A just has to go out of business. So when we think about the consequences of groundwater depletion, it's not as simple as you'll run out of water. It's more nuanced than that, in the sense of you will lose, some of the water users will lose access to water, and others will incur increased costs to access the groundwater. And so that's where the consequences of the depletion become, not uniform across the groundwater users. And that's where things can get kind of complicated in terms of policy decisions and what the response of water users will be. Because depending on who you are, B will say one thing, C will say another, and A will probably leave the area and just go do something else. And actually in the Ogallala, you can listen to people who talk about doing this and have gone through this when they've hit the fringes of the aquifer where they're not able to produce water anymore. So that's sort of more of what the water balance consequences would be. In terms of the degradation of groundwater quality, this is a big one, especially in coastal aquifers. And so when you look at groundwater, fresh groundwater coming in, it's lighter, it's less dense than salt water, and so it tends to be above the salt water. And when it hits an interface, the Gulf of Mexico or the Pacific or Atlantic Ocean, you have this lens there of fresh water overlying the salt water. The problem is once you start pumping, the ratio is if you draw the fresh groundwater down 1 foot, you'll have a 40-foot rise in the salt water on average. It's much more, I should say, if you're going to do the modeling, it's much more complex than that. But in general, that's what we were taught when we took the courses. That was the ratio. And so if you locate a well a little too close to that lens, you could be drawing the water down, and all of a sudden you'll have upconing of salt water in your well, and you destroy the water quality in your well. And this has happened in various water supplies, very close to the coast. And so there's many strategies that have been developed that deal with this. But basically what it comes down to is that groundwater is depleted, and then you ended up having very severe water quality concerns because of the depletion of groundwater. And this is something that has to be recognized and is recognized in a lot of water management, especially in the coastal regions across the U.S. Then we go into another issue, and this gets into the issue of capture. If you remember, if you're depleting groundwater, part of your pumpage comes from depletion and part of it comes from capture. You got to realize you're capturing from someplace. And so in many locations, and again, especially across the more arid west, the base flow in the streams is coming from groundwater discharging into the streams. And this becomes really important because not only is it the flow that sustains flow in the streams in the summer, where there may be endangered species or habitat for endangered species, it's also that it tends to be cooler water. It tends to be water that is more conducive to many of the trout fisheries across the west. And so what can happen here is that if you lower the groundwater level through depletion even a few feet in some areas, but often in many areas if you're lowering it by 10 or 20 feet, you've turned a stream that was gaining groundwater and maintaining a nice habitat to one that loses groundwater and dries up. And so as the groundwater levels decline, you can have some very serious consequences on stream flows and spring discharges. And Texas faced this in the Edwards Aquifer, where endangered species, they had to rework all of the groundwater management within the Edwards Aquifer and create a separate agency for the Edwards Aquifer Authority, which has taxation powers to deal with groundwater depletion in Edwards Aquifer that had nothing to do with not having enough water in the aquifer, and had everything to do with spring flows for this endangered species. And then finally, some of the most economically consequential issues associated with depletion are land subsidence. So I love the figure on the right. It's just a great figure. It's like 30 foot of land subsidence in the Central Valley of California over a 50-year period. And what happens here is that when we have groundwater, it's in between the pores of soil particles. And there's pressure in that the groundwater holds up. And if you pull the groundwater out, well, then the soil particles kind of compress because you don't have the groundwater there with pressure, helping the structural integrity of the aquifer. And so if you do this enough, you can run into problems where the ground literally starts sinking. And so you can have situations where this occurs over a very, very long period of time and get 30 feet of decline. Or you can have it in situations where the response is more rapid, and you can have shifting of land surfaces that can actually crack big water pipes, infrastructure, transportation infrastructure, homes, that type of things. And there's some very serious consequences associated with land subsidence. And in agriculture in the Central Valley of California, where it's been a real big problem, there's actually been situations where the surface canal systems, because of land subsidence, lose their capacity because they lose the slope to drive the water flow. So you end up with a situation where you may have to cut back your groundwater use due to depletion, and you've also created land subsidence, which has reduced your surface water irrigation delivery capacity. So you kind of get hit twice there for this problem. So land subsidence is something that really has to be considered when we're looking at depletion, and this occurs in many, many areas across the U.S. So how do we mitigate? Well, again, there isn't the simple, well, we're just going to do something physical and technologically and we'll solve the problem and walk away. We need to think of those solutions in the context of changes in governance systems and changes in financial incentives. So, technological approaches. Well, this is one where we can talk about, well, the aquifer's out of balance, let's try to bring it back in balance. So here, there's really two elements to that. You can either look at trying to increase the amount of recharge going into the aquifer, or you can decrease the discharge. Increasing the recharge or inflow to the aquifer can entail converting hard surfaces to soft surfaces, that is getting rid of impermeable surfaces and putting in green spaces that allow for more natural recharge. You can talk about using canal systems that deliver water in the summer and run water through them in the winter to try to induce more recharge. That's called passive recharge. And then you have aquifer storage and recovery. That's one where you're literally drilling wells and you're injecting water down in the aquifer. Oftentimes that's used more to elevate the water level to make it less expensive to extract water at later times, but it can also be used to try to just inject more water into the aquifer. The way to reduce water usage is you can look at your cropping systems and try to decide, well, are there alternative crops that are less water intensive that maybe we could be growing, or we can look at higher efficiency irrigation systems that end up not resulting in water not being used to grow crops. And this can be everything from putting in high efficiency center pivots to putting in better systems for understanding crop water demands as they change over the season. Now when we do this, it's really tempting to sort of say, well, we know the imbalance on the left side, and we know this, this difference between recharge and discharge and all of that, so all I need to do is match that. But you got to remember, the second you start changing recharge from other sources, you're going to start changing what those other sources of recharge and discharge are, and those have to be accounted for. So it's not something as simple doing one calculation of here's the imbalance and here's what we need to do. It's going to be thinking through the entire system of how you're going to reduce recharge and how it may affect the other water balances in the aquifer. So financial incentives. Basically, there's sort of two things here. There can be financial incentives put in place for farmers to change cropping systems to reduce the demand for water. And the other one is to have financial incentives to either get what we call managed aquifer recharge in place, or have higher efficiency approaches to irrigation. The danger with the higher efficiency is that if you're in systems that are dominated by surface water irrigation, and you convert irrigation application systems to high efficiency, what you've just done there is reduced groundwater recharge. And so there have been many areas, and the East Snake Plain is an example of this, where they went in and they put in higher efficiency irrigation systems and talked about lining canals and really losing less diverted surface water. Well, they were never losing it. It was just recharging the groundwater. And once they came in and they started pumping groundwater, they realized, now we're starting to see water levels go down. So when you're thinking about going more efficient with your water application, you really have to think about where's the water coming from, because as non-productive as high efficiency has been in the East Snake Plain in terms of reaching some sustainable water management level, the opposite is true when you're looking at systems where groundwater is the predominant source of irrigation, such as the Ogallala. Because in those systems, you're talking about, you're pulling water from the groundwater, so anything you're doing to reduce the amount of water you're pulling from the Ogallala, life is better. And so this is one where if we start looking at financial incentives, you may come up with something that works in one area that may not be appropriate in another. And again, you got to think of how all these things interact with each other, rather than thinking there's just sort of one straight answer that can be used for all of the issues associated with groundwater depletion. And finally, governance systems. It's interesting, I've talked to a number of directors here in every state I've talked to, so Oregon, Washington, California, Nevada, Idaho, on and on and on, have been talking about, our legislation is now dealing with this little issue associated with groundwater. Every one of them is talking about it right now. It's in Texas. I don't know if Oklahoma, maybe Kevin can address this, but it is really funny. There's something dealing with, we're going to tweak our groundwater governance system. So this is a big topic that's out there, very consistent across the West at least. And when we look at it, it kind of comes down again to the two general approaches, prior appropriations and decentralized regulatory approaches. Now, the states of Arizona, California, Nebraska, and Texas are using more of the decentralized regulatory approach, whereas the rest of the West is using prior appropriations, which is more of a state central regulatory approach. And when we look at these, there's advantages and disadvantages to each approach. The advantages to the prior appropriations doctrine is that there's clear rules for access to groundwater, and it provides a legal mechanism to reduce pumpage when depletion occurs. That is, if you're harming a senior water right user, it's like, that's what you signed up for. You got a groundwater right, you got nothing to complain about. However, I had a conversation with Todd Jarvis, and Oregon is trying to do that, and the lawsuits that flew when they tried to cut back groundwater pumpers, when it's completely obvious they're harming others in the prior appropriation system, is that Oregon backed off from it. So as much as we like to say the states will do this, it's very hard to find situations where it was actually that harsh, where they actually shut off groundwater users. It's usually something where they threaten it, and then things happen, and they move to new systems, and then there's some level of monetary compensation, and then they move on. So while prior appropriations may say they have the mechanism to do that, it's rare to see it actually implemented. The disadvantage of the prior appropriations, the first one is, prior appropriations is all about harming senior water right users. So there's no mechanism to address, well, what if you're impacting groundwater quality? Very little in prior appropriations that allows you to address that concern. And land subsidence, again, not. Now, you can create additional policies to deal with it, but prior appropriations by itself does not directly address that. And it also has this issue of that if you have non-sustainable groundwater systems, that is groundwater systems with so little natural recharge, they're just depletable, it becomes an interesting question is what does harming a senior water right user mean? Because the first person with a water right, anybody else that uses water will eventually harm them. And so that becomes one where you start to have to look at some modification to prior appropriations to make it work, and Kansas is doing something like that now. Now the regional groundwater control entities, well, the advantage there is that you can consider local concerns and conditions. That is, you can create regulatory targets that have to do with land substance or water quality or stream flows or spring flows. And Texas has those. If you look at some of the groundwater conservation districts, there's some that say, well, we don't want the water levels to drop below this point, so mainly a quantity issue. And others said, well, we don't want these spring flows to go below this point, so that's a surface water issue. And others talk about water quality conditions, and others talk about land subsidence. So you're actually allowing the regional, to deal with the issues that they're facing. The disadvantages is, in every such situation, and Doug can talk about this in California, typically you don't develop these entities until well after you have issues with depletion. So you're kind of chasing the problem instead of getting ahead of it. And the other one is that there really is no requirement in these. Maybe California can, I've seen some of the California Act, and they do seem to require sustainability, but a lot of the others don't explicitly require it in terms of their regulatory approach. They basically say, yeah, you don't have to be sustainable. Okay. So what are the take-home points? Well, we can go through, and these are just a summarization of what's in the report. The biggest ones is that groundwater is going to be, more stress is going to be put on groundwater for depletion for a very simple reason. If you look at the water use surveys, it's not like the U.S. is using more water now, but there's more competition between the various sectors. And when you look at why groundwater as opposed to the other sources, it is from a year to year dealing with the immediate problem at hand. The water table doesn't move that much in a short period of time, so it is the buffer. It is the insurance policy. And so using groundwater when we have a drought and streams dry up or something goes wrong in the streams, that is going to be where we're going to turn, and that's just going to increase our dependence on groundwater, mainly to meet the buffer. Even if we're not using more groundwater, the stress on the systems will continue to exist. The direct consequences of groundwater depletion, well, that increases the cost of groundwater for all users, but can also be somewhat unequally distributed. And there's many indirect consequences that have to do with affecting stream habitat, affecting water quality, and land subsidence. Groundwater depletion can be mitigated, but it has to be thought of in kind of an integrated fashion, and have to be thought of not just in terms of balancing the water levels, but how you're going to address groundwater governance, financial incentive, and how that's going to work with technological approaches to try to bring the aquifer back into balance. And you have to think specifically about the situation at hand and realize that something that's going to change a groundwater governance system to induce high efficiency irrigation systems, reduce pumpage of groundwater, and hopefully reduce the depletion of groundwater in one area, could lead to an exacerbation of a problem in another area if that means that it's going to reduce recharge to the aquifer, for example, from surface water diversions. And the bottom line of that, and this is what sets up the panel, is what this means is that there's going to be no silver bullet and no, my favorite phrase of all you got to do is, and it's not going to be something where there's going to be this national blanket, this is how you're going to deal with groundwater depletion, but groundwater depletion is going to have to be addressed by understanding what the drivers are and what the potential solutions are at a local to regional level, not something that there's going to be one simple plan that's going to be able to apply everywhere. And with that, we have three panelists, one from California, one from Arkansas is going to be discussing the Mississippi Embayment, and one from Oklahoma, and Kevin Wagner has been in Texas before, so knows an awful lot about the Ogallala. So we have three panelists that can speak to these issues in three areas where there's been significant depletion. So with that, why don't you guys come up? And I will start throwing questions at you and get a panel.
You want to click on through that last slide?
Oh, yes, sorry. There we go. So, with that, what I wanted to do is I'm going to start off with one question. If everybody else starts jumping in, I'm going to back off on the questions, but I wanted to get the discussion going. So I wanted to ask each of the panelists to just sort of briefly describe what the biggest issues in their state or region facing in groundwater depletion and what they're seeing as some of the more significant consequences. So I guess we'll go west to east, so that's the way we lined up. So Doug, you go first.
Okay. Sure, yeah, I'm Doug Parker from the University of California. Obviously, California's been facing some significant groundwater issues. We've been overdrafting in many areas of the state. The most significant areas would be in the Central Valley, particularly the Tulare Basin, as well as some of our coastal aquifers, especially areas where we're dealing with seawater intrusion as well. I think we have areas of the state, we get about 30% in a normal year of our agricultural water comes from groundwater sources. And in drought years, that number bumps up closer to 2/3, 60% or so. Partly because we're using less water, but also because we're using a whole lot more groundwater. So that the ratios kind of work out way with our situation. So groundwater serves two purposes in California. There are some places where groundwater is your primary source of water, and that's what you use every year. And there are other places where groundwater is a little bit more of a backup source that you use, increased use of it during drought conditions in terms of the impact to growers, but the impacts, of course, are with the overdraft coming on. California is one of those states. In 2014, we passed the Sustainable Groundwater Management Act, which requires setting up groundwater sustainability agencies at the local level. As John mentioned, we got that regional sort of local approach to try to let the local people try to figure out how to solve that problem and what are the impacts or what are the ways that they're going to do that. Estimates that have come out based on that is to get to sustainability, which our long-term goal is to be there by 2040. So we have to create these agencies, and we have to create sustainability plans, and then we have to have 20 years or so to implement them. Because it's not, as you mentioned, you don't just tell everybody to use 10% less, right? We've got to do other things as well. We've got to look at how those basins interact. We need to look at other ways to increase groundwater recharge and increase the supply side of it as well, and that takes more time. But some of the forecasts basically look at somewhere between 500,000, maybe 750,000 acres of irrigated ag coming out of production. So that's about 5 or 6 or 7% of irrigated agricultural land in California. And that's kind of after we do the good stuff, okay? So we're so far out of bounds, we've got to do all this good stuff, and that's only to get to losing 500,000 acres of land.
Kevin?
All right. Well, I'm Kevin Wagner. I'm with Oklahoma State University.
That microphone, you maybe pass it
Oh,
over.
yes, the microphone.
I'm Kevin Wagner with Oklahoma State University, the Water Resources Center there. And I feel like we have the most complex of the aquifers that we're talking about, in the fact that it covers 8 states, and with massive differences from top to bottom and east to west. The temperature difference between the sandhills of Nebraska and South Texas plains is about 20 degrees on average. And if you look at rainfall in its widest area in the east is 3 times higher than it is in the west. So you see tremendous differences in precipitation, evapotranspiration, how it's managed, and the level that it's farmed. So as a result of that, you see significant differences in the declines. So areas where we see the worst declines are in the South Plains near the Lubbock area, where you see declines in the aquifer levels of over 100 feet. The North Texas Panhandle near the Dumas area is another area where you see some really huge declines, and then Southwest Kansas near the Garden City area. So, but there's other areas like in the sandhills of Nebraska that you're seeing increases. A 2015 report that I looked at with Ogallala showed that the biggest declines since pre-development were probably in the range of 230 feet declines. In the sandhills of Nebraska, there's wells that have gone up 84 feet. So you see just tremendous differences in that. And recharge is a huge issue with the aquifer. In South Texas, the southern part of the aquifer, again, you're probably getting 1/10 of an inch or less of recharge annually. Sandhills of Nebraska, 6 inches or so on average. So, that really contributes to the complexity of the aquifer. But that region doesn't have a lot of surface water at all, so it is almost a sole source for most of that region. Once you get up into northern Kansas and Nebraska, you do start having some surface water bodies that can be utilized, but for the vast majority of the area, it is the sole source. So it is very critical to the economies there, those rural communities, that we do what's needed to sustain that aquifer.
Brian Haggard, University of Arkansas, Arkansas Water Resources Center. And so I've been asked to talk about the Mississippi Embayment. Really, you're looking at two different aquifer systems there. And first off, I'm a surface water guy, so I had to reach out to my contacts within the state of Arkansas to get a good handle on some of the issues, but I am aware of those. You have the alluvial aquifer, which is a relatively shallow aquifer. We definitely have depletion issues there. We are fortunate such that when you deal with alluvial aquifers, the recharge is typically a lot faster than when you're dealing with some of these deeper aquifers. In Arkansas, we have a really good synergy between the various entities within the state where they're wanting to see the impact of management practices. And so what they're doing is they're going into small focus areas where they know they have depletion zones, the Cache River, the Grand Prairie, and they're implementing management practices to conserve water use and change irrigation strategies, and they're measuring the response of that. And so they're trying to go into areas, change things, change what they're doing, see what impacts that's having over time, so that they know how to expand those best management practices and water conservation strategies across the rest of the state. And so that's something that's really unique. I will put a plug in for the USGS. They're doing a huge project on the Mississippi alluvial plain, and they're going to have real-time graphs and different things like that come up for that. So that's going to be an incredible resource for that issue, for that area that stretches from basically from Missouri down to Arkansas, down into Louisiana. Basically in Arkansas, you see that if we're having groundwater issues, what you see happening is we have surface water. We're building ponds, and we're really moving to more conjunctive use and capturing our tailwaters and storing that water. And you see that in the areas where we do have groundwater depletion. There's a lot of that going on. If you see the ponds, it's because groundwater is becoming an issue in that area. That or it's an aquaculture facility, one of the two. That's what you see in Arkansas. One of the other things we have that I think is really unique in the Delta area, it's called the Delta Flux Network, and it's a system of eddy covariance towers. And so we're actually measuring ET, but along with that, what are the gases coming out of the landscape due to different irrigation practices? And so I'm going to still kind of like the term that Doug was throwing around. It's definitely climate smart agriculture. We're looking at how these irrigation practices influence our carbon footprint. And so that's a really interesting piece that's going on in the Delta or the Mississippi Embayment as well.
So, any questions? I mean, I could sit up here and drill these guys for hours. Okay, Jim.
So Doug, so Sigma's been passed, so they've started putting in the, they've started building the infrastructure now, and it's pretty still early days for Sigma, but where's that farmland going to come out? Is it going to be the almond groves that have moved down towards the attached piece, these marginal areas that never really were well watered, or what's the plan?
So as I mentioned, we've got local government agencies that are being formed to manage those. So we've got, I believe there's 127 basins in California that fall under the Sigma Act that basically is working towards groundwater sustainability. As you mentioned, what does groundwater sustainability mean? You can go and read the act. They define it as not doing 6 bad things. So I'll leave it there. So we've got 127 basins, and we're supposed to set up groundwater sustainability agencies. So we're setting up the governance infrastructure right now, and we're not going to have 127. Okay, we're going to have way more than that because we didn't tell people how they had to draw the boundaries. So I think I was just looking at a report in the Central Valley. We've got, I think, 15 main basins, and I think there's about 120 GSAs of life just in that area. So going to the graphics you saw earlier of water moves a lot more laterally than a lot of people think in groundwater basins. you know, you're gonna have a groundwater basin with 7 agencies managing it, fighting over, you know, which direction is that water going down there? Is it coming into my agency from your agency? Because then I wanna talk to you about that. Is it going the other direction? In terms of taking land out of production, I mean, there isn't any set plan for that. I mean, it's, you know, it's gonna be growers' decisions. The GSAs are gonna have to decide how to allocate the groundwater rights, okay, in some way. So again, currently groundwater is, you know, if you got a big enough straw, you can take the groundwater. That's gonna change with this. So there will be some allocation scheme. They can do it however they want though. Some could say, you know, divide by the you know, what's our yield divided by the number of acres, and everybody gets, you know, 1.2 acre-feet per acre. And if you want to grow almonds, then you need to only use a third of your acreage or whatever the number put out. Others may do it based on some historical pumping. So it's going to be interesting to see how that works out. We're trying to, you know, do the best we can with things like increasing recharge. So there's a lot of work. In fact, today there's a big meeting in Sacramento to look at what are the research gaps in terms of using agricultural land to recharge groundwater during winter flood flows, basically. You know, how long can you flood an almond field before you hit the almonds? Can you use, you know, it's one thing to flood fallow land or land that's you know, not being used during the winter, but flooding vines and almonds and other things, it can be done. But there's a lot we need to understand to do that. So that's one of the ways we're hoping to increase that recharge side of it. But even after all of that, as I mentioned, you have this problem. Other things we're looking at doing is trading programs. So, you know, can growers trade groundwater within a basin, across basin lines, to help lessen the economic impacts as they're able to do that. And then the final thing that I'm seeing some action on is, you know, if you face the reality that you're going to take 500,000 acres out of production, there's two sides to that question. One is, which is the best 500,000 acres not to take out of production or to leave in production, the high quality lands, things like that. But the other is, land you do take out of production, what do you do with that? The report here talks about dry land farming. It's not really much of an option in most places in California. So you're going to be putting that land back into some, hopefully, long-term natural state. And is there a way we can do that smartly to increase habitat, to work with, and other ways to at least not cause additional problems as well, because abandoned farmland, especially in very arid areas, leads to air quality problems and things like that. So I don't have an answer of how that's going to work out. It's going to be messy, and it's going to be interesting, but we're trying to bring as many of these other tools to play to lessen that impact.
So what you wrapped up on is that the big issue of, you know, what do you do with the basic farmlands abandoned? I know, Kevin, you've been involved in this in the Oglala through the OAP and the Colorado, you know, State OCAP project where that discussion's come up. Do you want to talk about some of the ideas that have been coming up through those programs in terms of conversion of lands, not just to dry land, but also converting it back to, you know, how should I say, not being disastrous?
Sure. Well, we recognize that ultimately the Oglala region will eventually go back to its original state of not being irrigated to a great extent. So we've been thinking about, you know, how do we make soft landing for that region and maintain those rural communities and their economies and ag production in those areas. And so we're looking at a variety of different things. You know, for the transition time, the deficit irrigation is certainly a big area that we need to do a lot more research in, and there needs to be more options with the insurance programs like the report mentions. Right now, there's not that ability to a great extent to go to a deficit irrigation type scenario. Development of the crops, more drought and heat-resistant crops is another area. And, you know, my hopes is that we can extend the life of the aquifer long enough that our geneticists can develop those crops that can maintain the production and profitability of that region, that once we do get to a point where it's no longer feasible to pump from that aquifer, that we can have some viable crops ready to go. But, you know, before we started irrigating, this region was producing wheat and cattle, and probably 100 years from now, 200 years from now, we're going to be going back to something looking like that. So how do we increase the productivity of those rangelands, and the conversion of that cropland back into rangeland is another big topic of discussion, because you know, those soils have changed drastically since they were originally broken out. You've lost a lot of organic matter and the nutrients. So how do you make that conversion? We've seen in other areas in Oklahoma where the cropland's been abandoned that those are about half as productive as the native grassland sites. So, you know, how do we deal with that issue is something we're looking at, the soil health aspect there. And, you know, this is really a long-term potential, but using alternative waters is another area that we're doing a lot of work in. There's a lot of oil and gas production in the area that produces lots of produced water. It's really nasty stuff right now. It's very expensive to treat today, but who knows, with advancements over the next 20, 50, 100 years, we may get to a point where before the aquifer is gone, we'll be able to have the ability to use those other sources to continue the productivity in that area. So those are just some of the things that we've been looking at, and I think have some viability for long-term viability of that region.
I want to direct a question to Brian. Could you talk a little bit more about some of those management practices that producers are working with testing? And I asked that question maybe I posed to John earlier in one of the briefing sessions in light of the recent farm bill and thinking about the next farm bill. Are we seeing certain types of conservation practices that are better in terms of both water management, whether it be surface water, groundwater? What are some of the things, lessons learned coming out of that? Are we seeing certain emerging best management practices that maybe need to be replicated in other areas that might have potential to extend or better manage our existing water supplies?
I mean, for us in Arkansas, the majority of our irrigation usage is going to be on rice, and there's been a lot of research into alternative wet and drying. They've been doing it in Mississippi for years, but now we're starting to get some really good data in the alternative wet and drying. It uses less water just because you're not maintaining the flood pool in there. You're letting it drain down and go down and dry, but that also ends up reducing methane emissions greatly, like significant reductions in methane emissions. So there's a synergy there for the carbon footprint for that crop. Row rice, right now with the commodity prices of rice, there's a lot of people that are, you know, instead of going in and plow boarding and putting in the levees, you know, after soybeans or something like that, they're just growing row rice, and they're willing to sacrifice the yield gains because of the ease in management. And so those are some of the things that are going on. One of the biggest things we're doing in Arkansas is we're putting flow meters on our wells. I mean, everyone's supposed to regulate how much water they're using, but that's not been the practice. And so a lot of extension efforts and statewide efforts with NRCS and our other entities that deal with the groundwater wells is actually putting flow meters on there so farmers can actually know what they're using. And then from there realize, you know, can they start dialing that back? You know, like John was saying, you can't be on the 10% of the one side of the equation, right? Because you're going to lose your crop. So you have to be on the other. But they don't know if they were 90% over or 100% over on what the crop needs because they don't have flow meters on there. So that's been one of the big practices is just once people start measuring what they're actually utilizing, they start managing that resource a little bit differently than just turning it on and not understanding.
That's probably a naive question. That's what you get when you let administrators and a water expert come to events like this. But it seems like that a lot of the vast majority of the asymmetry in the depletion versus discharge is due to technological pumping technologies. But yet a lot of the recharge discussion is management practices and mitigation. are there any technological processes in either currently in use or in the near horizon that can be used to increase recharge, especially in areas like in the Ogallala? Major areas of the Ogallala are out of drought, but that's very different than recharging those aquifers.
I'll talk briefly and then let Doug talk on that. For the Ogallala, that is something that's been looked at and maybe even tried out. I know there were some studies years ago to see if you could drill wells in the bottom of playas and let that water infiltrate directly down into Ogallala. Unfortunately, I think a lot of those wells clogged up pretty rapidly, and so you weren't able to have very much recharge that way. You know, really the bottom line for that is the expense of it, and having a source of water for doing that recharge as well. So, you know, probably at least in the southern portion of the Ogallala, that doesn't appear to be feasible, at least with what we have today. Now, looking down the road where maybe we have some other marginal water supplies that we're able to treat inexpensively, maybe there will be some opportunities for that in the future, but you know, right now the economics just don't work out.
Yeah, I would say in California there's probably two different issues to look at there. One is just the physical part of recharging. I mean, it was mentioned like injection wells or things of that nature. We've been, as I mentioned, going more towards how can we use additional land to get recharge. It's cheap, it's not too tough to do. You just got to find the right land, and you got to look at what's on that land when you're doing the recharge. But another way to look at your question is, especially in a place like California, is if you're going to increase groundwater recharge, where does that water come from? And if you're already using all of your surface water, you don't really have water left over to increase groundwater recharge. Now, you know, I mean, the storms they're getting today are big storms, and so what we're looking at is we get big storms and our river flow, you know, goes up tenfold. Okay, well, we don't have systems to capture all of that water behind dams and reservoirs and stuff, so that's why we're thinking, let's get it out on the land and get it soaking in and try to increase that way. But to go to your technological question, if you can better manage your surface water and squeeze some more surface water out of there, then maybe there are some areas you can do groundwater recharge as well. So one of the things, you know, one thing we're looking at right now is better reservoir operations in California. So we're using, you know, reservoir operation, because our reservoirs are both flood control in the winter and water storage the rest of the year. So can we figure out how to better manage that flood control aspect of reservoir operations so that we don't have to dump a lot of water if it's not really necessary? So I was just, in fact, reading today, you know, that big storms were coming into California. They're starting to lower several of the reservoirs. The more you know about where those storms are going and how much water they're bringing, the better you can manage that reservoir and say, well, that one's going to miss us. We don't need to dump as much water. You know, where that one's really coming hard, we need to dump water. So I think there's, when you look at the connection between all the waters, ground, surface, saline, even, you know, ocean and desal, wastewater reuse. I mean, you have to look at that entire picture and say, we may not be able to do as much in this area, but we can apply new things over here that's going to free up or lessen the strain in those areas as well.
And all that, in Arkansas, we're a water-rich state. Our problem is the surface water is not always where we need it to, you know, increase recharge in the alluvial aquifer. And so we're trying some projects where we're trying to move water from the White River Basin over, but that just becomes, I mean, it's cost. And then is it cost effective to do that versus other things? And so we've had a really large project trying to move that water, but it keeps hitting roadblocks.
Yeah, and as you've seen in California, we've already paid a lot for infrastructure. But our infrastructure is designed with certain things in mind. If we're going to use it for other purposes, we might need different infrastructure as well. So moving those flood waters is not as easy as you always think if you don't have that.
John, as you were describing water flow, what struck me was like matter, it can't be created or destroyed, but it changes forms.
Yep.
Right? So as the polar ice caps presumably melt and so forth and so on, will that become groundwater, or is it all just going to go into the ocean?
That's an interesting question. Well, I mean, so when you look at the ice caps down in Antarctica, initially there will be part that will melt, but probably from what I've been reading, the big thing is going to be catastrophic failure and it'll slide off in a frozen state. So it'll be going to the ocean. After that, that would be quite consequential. I do know, when was it, the mini ice age, like 500 years ago, when they had, the theory is it was triggered by a significant ice cap sliding off the ocean, disrupting ocean currents, and causing a cooling in Europe for some time. And so if you look at something like the West Atlantic ice sheet sliding off, it would be so disruptive to ocean currents that, yeah, it would impact groundwater, but boy, I have no idea to predict exactly how it would impact groundwater, because it would impact the entire Earth's hydrologic cycle. Everything would be impacted in terms of where water was falling, what the temperatures were, what the potential ET would be. So as the ice caps melt, if they melt really slowly, yeah, it's going to go to the ocean, and things would probably, you'd have rise, but things probably wouldn't change dramatically quickly. But if it's what a lot of the scientists keep predicting, which is going to be, actually a catastrophic failure of an ice sheet going into the ocean, kind of all bets are off.
On that happy note.
Never know.
This may not be a happier note, but I haven't read the report, and I'm sitting here at Farm Bureau, and I think the economic part of this, just we haven't talked enough about that. And Doug's an economist, so maybe he'll want to comment, but as biophysical scientists, we can see, gradients and continuums from full irrigation to dry land. But from a farmer's perspective, they've got a debt equity situation. They've got irrigated land that's worth $5,000 or dry land that's worth $1,000. Same for the way the county assessor looks at that land, and they're making decisions today to go to their banker and farm another year. And so I think it's easy for us to say, we can tweak the governance or we can tweak the irrigation practices. The farmers have got to go get a loan based on having irrigated ground, and they've got to live to fight another day. And we know we've over-appropriated aquifers, and we've done that as a society, right? Ogallala, we're growing beef and dairy. I mean, it's a livestock system out there that we're supporting. And, tweaking around the edges is not going to take care of the farmers nor the aquifer here. I mean, we're looking at some systemic changes that are going to happen. And I don't know, whether it's farm bill mechanism or we let these guys go out of business, but for a farmer to say, well, I'm going to go into deficit irrigation and I'm going to declare some land dry land. Doug, I don't know if you want to comment, but it doesn't work that way.
Well, I will comment from the perspective of the policy tweaking.
Need to get
what
to
I've
the mic.
What I've noticed in terms of water policy, and especially in agriculture, because the investments in agriculture, I mean, if you go and invest in developing a field, whether you're using irrigated or dry land, you're in there for a decade at least. And so if you're talking about significant policy changes over a short period of time, that's probably the worst outcome for farmers, because they have to have some level of assurance that the rules aren't going to change that much from this year to next year. So when I look at these, actually tweaking around the edges may be the only way to go here, because if you make significant policy changes in 1 year, you could have significant disruptions in what farmers are able to avoid. So you've got that side. Then the other side, I think one of the things is, and this is where getting involved in the study that, the Ogallala, the OCAP, as we affectionately call it, is interesting, because you're talking to a lot of farmers that have been dealing with how are they addressing transition during the depletion of the aquifers. And there's some interesting things coming out about that when you start looking at what were the crops grown in southern Ogallala 20 years ago versus what's being grown right now. And we have seen huge changes in the cropping systems. And we have seen the influx and the growth of the dairy and the livestock industry there. And I think there's lessons to be learned from that if we treated what has been going on in response to depletion as kind of the experiment of what may work in other areas. And the Ogallala has been doing a good job of capturing that. But I think it's one that, phrasing it more as less about solving the problem and more about understanding how are these systems transitioning. Because it's very clear in the Ogallala that there's been winners and losers. If you look at the region overall, it's not devastated. I mean, there's a lot of adaptation and there's a lot of angst about what the future's gonna be. But there's also been a lot of innovation in terms of just looking at different types of crops, having, new crops, varieties developed, and changes in practices. And I mean, that's one where I think the initial project of the CAP project focused on the overall has been great. And it's one where the discussion seems to be moving towards not just what are we going to do next for the sake of doing more research, but what are we going to do next, because it started getting to the point of understanding that this is all about transition and that we do have enough lead time there, and we do have enough information from what's been going on for the last 20 years to sort of at least make some predictions and start looking at what can be effective changes in the economics department, what can be effective changes in terms of both local policy and state policy, and what can be effective in developing new technologies. At least that's my perspective on it. And it's going to take a while, but I look at that as not so much despair, but just how resilient that region has been so far to depletion. And I think just sort of with more involvement of research and outreach and education, it can be optimistic.
And I think my response would be, markets are already reacting.
Yeah.
Okay, so if you go to the Central Valley of California, land prices are changing today, depending on what your water sources are, where they think that's going. But markets also know that we've got a 20-year implementation period. So, if I've got another 10 years left on this almond crop, I can start adjusting for it. So we're the whole goal. A lot of people were like, wait a minute, how are you going to get to sustainability in 20 years? That's way too long. We need sustainability tomorrow. Well, we know we can't do that. It's just too disruptive. But the markets are going to be adjusting. Farmland values are going to change. That's where it's really going to hit the most. There are discussions going on about, well, what can we do to help lessen the impact of this on the individual? There are people out there who are like, well, you made a bad decision, tough luck. A lot of other people don't really feel like that's the right way to go, that, we want to figure out a way to help, not just the growers, but the communities as well. You got unemployment impacts in different communities, shifts in schools and all kinds of things like that. So I think there is a conversation that's more beginning than anything at the, hopefully the federal, but also state and other levels of how do we fairly, share the pain in this, because there is going to be some loss in value to growers and to farmland. But on the other side of it, we're paying pretty heavily right now for some of that, subsidence shift. And it doesn't go down like this. It goes down like this in a crinkle, right? So, if everything went down the same amount, you might not have a problem, right? So, but it doesn't. So, that's quite expensive. Communities running out of water. I think there's, something, it's not all because of this, but, we've got about 300,000 people in California who don't have good, reliable, safe drinking water. Some of it's groundwater depletion, some of it's pollution and other things going on, but we need to kind of look at those communities.
But notice we haven't talked about food productivity or food sustainability.
Right, yeah, and then that's the other side of it, is this, when you look at a more, global kind of situation, people have looked within, okay, so California goes down by 5%, well, we can do an economic analysis of that, and that's actually not gonna be a huge hit on food prices, but we've got groundwater depletion all over the world, all over the planet right now, and that's a different story, and we need to be thinking more and more about that, for sure.
Can I ask one more question?
Sure.
Hopefully quick, short answers, because this got brought up. We did the presentations for House staffers, Senate staffers, and it sort of brings up this role, since the states actually own all of the water and set the rules, and we're talking about groundwater depletion. What is the federal role in terms of helping address this problem, at least from your guys' perspectives, addressing sort of three regions that are facing this?
Yeah, I think that's an excellent question, because water management is all taking place at the state or the local level, where's the federal role? I think it goes back to just exactly the previous conversation, helping to find ways to more equitably spread the pain, or more equitably find, the wins and the loses out there. Certainly, research and outreach and education and other things. the federal government is involved in terms of helping to do the management part. As people mentioned, I mean, USGS is a big player in providing technical assistance and things, but I do think most of that, you know, work has to happen on the ground in the local area, but the federal resources, which is I think what most people would say, not just monetary, but, you know, research information, other things like that. And then, I mean, well, maybe more in the
I mean, I would say
Ogallala, but in California, we don't have any cross-boundary issues in California, so I'll let you guys talk about that part.
What I would say is the cost share programs at the federal level that are very important to the state of Arkansas in getting these conservation practices implemented.
I would echo that as well. Those conservation programs will be critical in moving things forward. But I really think the research and extension, and of course I'm coming from a land-grant university, but I think they will play a critical role as well. There's a lot that we can do to improve the technologies out there. There's a lot that we can do to improve the crop genetics. And there's a lot of extension and education that needs to go on to help the producers to adopt these new technologies. You know, you look at across the Ogallala region, and most states, 11% of the farmers or less are using sensors and irrigation schedulers. So, you know, there's obviously an issue there, a barrier that we need to help those producers overcome. Maybe it's the technology. We need to make it easier to use and more reliable. But, you know, those are some of the things that I see as a role for the federal government. And then the crop insurance. You know, I also think that that is an issue that needs to be dealt with as well.
I want to say thank you to not only to John, to our panelists, and to all of you for being here, being a part of this program, this conversation about, and I like your question. I think maybe we can take this conversation across the hall and be a little bit more philosophical over a glass of wine or a beer and some foods. I invite you all to enjoy us across the hallway.